Okay, the next one is this. There is a group in which we have two elements A and B that commute with each other, and also there the intersection of the cyclic subgroups generated by them is trivial. We have to prove that the group has an element whose order is the least common multiple of the orders of A and B, which we are denoting by m and n respectively. So in the solution we will show that the product of A and B, AB, is one such element. So let us see the solution. Let K denote the LCM of m and n. So K is the least common multiple of m and n. Let K equal to alpha m equal to beta m. Because K is the common multiple, so it will be multiples of m and n, where alpha and beta are positive integers. Since A and B commute, we have AB whole to the power K is equal to A to the power K times B to the power K. From the fact that they commute, we have this thing. Now K is alpha m, and also at the same time it is beta n. By using one of the rules of exponents, beta m is the this is A. M is the order of A and n is the order of B. So this one is e to the power alpha times e to the power beta. So this is equal to e. Okay, so the kth power of AB equals the identity. Now suppose there exists an integer I such that I is a positive integer, it is less than k, and the ith power of AB is also equal to identity. Suppose then, since A and B still commute with each other, we have this which implies A to the power I is equal to B to the power minus I. But A to the power I, being an integral power of A, belongs to the cyclic subgroup generated by A, and like that b to the power minus I belongs to the cyclic subgroup generated by B. Since they are the same element, so that element belongs to both this one as well as this cyclic subgroup. So this common element belongs to their intersection, which is given to be the trivial group. We thus have that is a to the power I equal to E and b to the power I is also equal to E, because b to the power minus I is E. So if you take inverse on both sides, you will get this. This implies, okay, so because a to the power I is E, so the order of A divides I, that is M divides I, and from this equation we get the relation that the order of B divides I as well, that is N divides I. Hence, so I is a common multiple of M and N, so the least common multiple, which is K, also divides I. But this is a contradiction because I is a positive integer less than K, so how can K divide I? Thus, our supposition is wrong. That is, no positive integer I smaller than K can make this equation true. That means K is the smallest positive integer for which we have this. So, order of AB is equal to K, which is the LCM of M and N. So, this completes the solution. Next, suppose that A and B belong to a group G. then A and B commute. That is also given, and further their orders are finite. What are the possibilities for the order of AB? Okay. Let M denote the order of A, N denote the order of B, and let K be the LCM of M and N. Okay. Now, just like the previous exercise, here also A and B commute. So, from the previous solution actually, from the solution to the previous exercise, we have this. Note that everything is not like the previous exercise. In the previous exercise, this condition was given. Which is not necessarily true now, but looking at the previous solution, you can see that we made use of this condition only after showing this thing. This is independent of this hypothesis. We don't really need that to show this one. So this is anyway true. We just need A and B to be elements of finite order that we have here. So this is true in this case also. Hence, this divides K. So this can be any positive divisor of K, where K is the LCM of the orders of A and B. We can say only this much about the order of AB, because note that unlike the previous case, we don't have this. This is not necessarily true now here. So we cannot say that the order is exactly equal to K. We can at most say that the order divides K. Okay, next. Exercise 40. Oh, I think I missed something, no? Did I write that? What I missed is this. in exercise 41, at the end of the statement, I don't remember if I have written it or not. Show that, so the statement is like this: show that this need not be true if A and B do not commute. Okay, so for this, what you do in the solution after you get to this stage, you then, I'm not going to do it entirely. You look in the dihedral group D3. In this group, since this group has only 6 elements, it's very easy, it's a small group. In it you find 2 elements A and B. They will have finite order, of course, and such that the cyclic subgroups generated by those 2 elements intersect trivially. Then it's not necessarily true that you will find an element in D3 whose order is the LCM of the orders of A and B. This you try, okay. In D3 you will find the thing. Okay, so I forgot about this. Anyway, let us continue with exercise 43. Suppose that this starts just like exercise 42. Suppose that A and B belong to a group. Again, A and B commute and these 2 orders are finite. Prove that G has an element of order this. So what is the difference between this one and exercise 41? There also A and B were group elements that commute with each other and have finite orders. Okay. Oh, there we had that additional condition that the cyclic subgroups they generate intersect trivially. Here we don't have that hypothesis. Still the result is true that G has an element of order that equals the LCM of those 2 orders. There also we were supposed to show that there is an element in G whose order is the least common multiple of K. So this is more general. Okay, let me just first see whether I am missing something. No. Okay, so we start by denoting these things by some letter. Let M be the order of A, N be the order of B, and K be the least common multiple of the orders of A and B. Also, let D be the greatest common divisor of M and N. That also we will need here. Then, since M and N are positive integers, we know this number theoretic result that K is equal to Mn divided by D. If we multiply the two integers, divide the product by their GCD, then we get the LCM. And further, we know this. The GCD of M by D and N is 1. That also we know. Because if we divide an integer by the GCD, greatest common divisor of M and N, then after the division, besides 1, nothing is common. I mean, as far as the divisors are concerned. So there is no common divisor between M by D and N other than 1. Of course, we are talking about positive common divisors. Now, by what is this result? Theorem 4.2. We have what is the order of the power a to the power d? We know by that theorem that this order is the order of a divided by the greatest common divisor of the order of a and d. Okay, now this is equal to, this is m, the numerator is m, and the denominator is this. Now since d already divides m, so GCD is d. So this is equal to m by d. Okay. Next, let C be an element common to these two cyclic groups, the one generated by a to the power d and the one generated by b. Then C is equal to a to the power id. Have I used I here somewhere? No. And at the same time, C is also a power of b. for some integers I and j. Okay, now what we can do, we can again apply theorem 4.2 to find the order of C in using these two different expressions for C. By theorem 4.2 we have okay, in calculating this one, have I used, yes, this is interpreted as the ith power of a to the power d, because we already know, we have calculated the order of a to the power d. So by that theorem, and d, sorry, so this is what m divided by d divided by GCD of m by d and d, and at the same time if we use this expression, n and no, I think okay, we don't have d here, we will have I, sorry, and here we will have j. Okay, now look at these two things. This is the order of C. At the same time, this is also the order of C. Hence, okay, now the left hand side is a divisor of m by d, a positive divisor, and the right hand side is a divisor of n. Since the left hand side in the above equation is a positive divisor of m divided by d, and the right hand side is a positive divisor of n. So that means this common positive integer is both a positive divisor of m by d and n, but we know that m by d and n are relatively prime, and these are relatively prime. We must have this, both of them must be equal to 1. That is the only possibility. This part we are not going to use it because we have m by d and it's more complicated than this one. We just considered this equality. So n is the GCD of n and j. Now GCD of n and j divides both n and j because it's a common divisor. So in particular GCD divides j, that means n divides j. Which implies n divides j. But then since n is the order of the element b, so c is equal to b to the power j. N divides j means j is a multiple of n. So using the fact that n is the order of b and using the rules of exponent, this will be equal to e. Hence the cyclic groups generated by a to the power d and b intersect trivially. Okay, so this condition that we had as a hypothesis in exercise 41 is now true for these two elements. What else is true? Since a and b commute, a to the power d and b also commute. So by the solution to exercise 41, order of this product a to the power d times b is equal to the LCM of the order of a to the power d and the order of b, which is equal to the LCM. This one we have already calculated. This is m divided by d and this one is n. Now since these two numbers m by d and n are relatively prime, so the LCM is their product times n, which is mn divided by d, and that is nothing but k. And recall what k is. K is the LCM of m and n. So this is an element in our group which has order this. So we have proved its existence. So here the solution ends. Then exercise 44. Let f and f prime be distinct reflections means in a dihedral group, in this dihedral group D21. What are the possibilities for the order of this product f prime? Okay, for that one we proceed like this. We are going to recall an exercise that we saw previously. By exercise 41 of chapter 2. F prime is a rotation in D21 that is different from the identity rotation or not. Actually, the fact that this product is a rotation is not what is the content of this exercise. In the exercise we showed back then that this is not equal to R0. Since it's a product of two reflections from yet another previous exercise, we know that it's a rotation. That comes, I think, even before this one. Anyway, so this is the fact. So we know this is a rotation. We don't know exactly what rotation it is, but we know that it's not equal to R0. It's not the identity element. Okay. Thus, since it's a rotation, so it will belong to the cyclic subgroup generated by the smallest rotation. I mean, we already know that in any dihedral group, the rotations form a cyclic subgroup whose order is half the order of the whole group. For example, here there are 42 elements. Among those 42 elements, 21 are rotations and the other 21 are reflections. Okay, so if f prime belongs to this group 360 divided by 21, this is the smallest angle through which, if we rotate a regular polygon with 21 sides, then that is a symmetry. This cyclic group minus R0. Okay. So now note that although our original group D21 is not cyclic, but now we are in a cyclic group. So we can now apply the results that we know about cyclic groups, or rather results about orders of elements in a finite cyclic group. Since this order is equal to 21, we thus have by this particular result. Corollary 1 to theorem 4.2. which says that the order of any element in a finite cyclic group divides the order of the group. So that means the order of f prime should divide 21. So there are 4 possibilities. Either the order is 1 or 3 or 7 or 21. But it cannot be 1 because f prime is not equal to R0 and R0 is the only element. The identity element is the only element in any group whose order is 1. Any other element, any non-identity element must have order greater than 1. It may be infinite also, but not equal to 1. We thus have three or equal to 7 or this is equal to 21. If this is the case, then f prime generates this cyclic group. It's a generator because that is the order of the cyclic group. So these are the possibilities for the order of f prime. Okay, now we come to a problematic exercise 45. Let's first see the statement and then I will tell you what the problem is. Suppose that H is a subgroup of a group G and H has 10 elements. If A belongs to G, and the 6th power of A belongs to H, what are the possibilities for the order of A? Okay, there is nothing wrong with the problem itself, but the difficulty is here. Whatever let me just tell you what the thing, what the difficulty with all these exercises are. You probably know there is something called Lagrange's theorem, which in this book is still far away from us. we will have to go through many more things before we get to this result. The statement of the theorem is very easy. Say you have a finite group G and you have a subgroup H of G, which in this book is being that statement is expressed like this: H is a subgroup of G. Then H is also finite, so the orders of G and H are both finite. This theorem says that the order of H divides the order of G. Okay, and this makes life very easy. Now, since we don't have this theorem, we have no right to use it, of course, because we are not supposed to know it yet. We don't have it yet. We have, however, proved in this chapter the cyclic group version of this in the fundamental theorem of cyclic groups, where we proved that if G is a cyclic group, then H is also a cyclic group, and if G is finite, then the order of H divides the order of G. So here you can see that we have used this cyclic group version of Lagrange's theorem. It's because our element f prime is in this cyclic group. So in this cyclic group, that theorem is true. And a consequence of this theorem is that the order of any element in a finite group also divides the order of the group, which is very easy to see once you have Lagrange's theorem, general Lagrange's theorem. What you do, you have a finite group G, you take an element G in G, which also will have finite order. Then the order of the cyclic group generated by G, is equal to the order of the element G itself. Since by Lagrange's theorem this thing divides the order of G, so the order of the element also divides the order of G. So this we proved. We have already proved this for the case where G is a cyclic group. That's what we are using here. Now that is not the case here. You see, H is given to be a subgroup of G and H has order 10. Okay. If A belongs to G, A is some element in G such that this sixth power of A to the power 6 belongs to H. What are the possibilities for order of A? Besides this corollary to Lagrange's theorem, there is another thing that can be proved using Lagrange's theorem. It is that if you have a finite group G and you take any element G in G, then this equation is true. And in fact, this result follows from this one, because since order of G divides this, so order of the group will be some multiple of the order of G. So you will be able to write it like this. And then you use the rules of exponent and you can see that this becomes identity. Now if one uses this, then this exercise is very easy. Let us see how. Let us first assume that we know Lagrange's theorem in general, and in particular we know that result. Now because A to the power 6 belongs to H and H is given to be a finite group whose order is 10. So this should be true. According to that thing we were talking about right now. So that means this should be true, and then use the rules of exponent to have this equation. Now from this equation you can then say, from the results that we already know, truly know, that order of A should divide 60. That is, the possibilities for order of A are these, that it will be some divisor, some positive divisor of 60. Now if one looks at this particular group, the group of integers from 0 from 0 to 59 under addition modulo 60, that is a cyclic group whose generator is 1, a cyclic group of order 60. In this group you will find elements of all possible orders, that is elements of order 1, elements of order 2, 3, 4, all the divisors of 60 can be attained. I mean, those orders can be realized by some elements in this. So it's not that some divisors will never appear as orders. This is an example where elements of all possible orders appear. All of these things are fine provided we have this result, which is a consequence of Lagrange's theorem. Now the problem is this. Okay, so this is a strategy which we cannot apply because we don't have Lagrange's theorem. We only have it in a cyclic group, a finite cyclic group. So the problem now here is this. You have to somehow prove that this is equal to identity. I have seen on the internet also that that's how the solution has to be written. But I don't know how people are simply writing this. Since a to the power 6 belongs to h, so this is true because order of h is 10. We don't have that result yet. Maybe they have forgotten that thing, or maybe they are following some book where Lagrange's theorem is available. Now, without using Lagrange's theorem, you have to show this. I have so far been unable to show this. However, there are two results which may be of use in showing this. I don't know how far, but somehow I feel these two things will be of use. One is, we have already come across these things. Exercise 50 of chapter 2. This exercise says this. The number of non-identity elements in a finite group G that satisfies this equation. is a multiple of 4. In the text it's wrongly given as 5, but it will be 4. In fact, the corrected one we have already solved because it appeared in chapter 2. This is one result. Another result is from chapter 3, which is exercise 59. Which this is much simpler than the previous one. In a group of even order, there is an element of order 2. Why do I feel that these two exercises will be of use in showing this? It's because you see, order of h is 10, which is 2 times 5. If we assume that Lagrange's theorem in general is true, right now, prematurely, if we assume without any proof, then it says that any element b in H must have order either 1, because it should divide 10, or 2, or 5, or 10. From these things, we will somehow be able to show this. I feel like that. It may not be necessarily true also. I mean, even if you manage to show these things, you may not be able to show this, because this is a consequence of Lagrange's theorem, which is very fundamental. At the same time, it's not very, what can I say? It's not a very difficult or deep theorem. It's quite fundamental, and in a sense it's very easy. So bypassing that theorem and somehow being able to show that this thing is true is very unlikely. Although the way this exercise has been given, it seems like this is the only way, because the answer is just that. Order of A should be a divisor of 60, and in that particular case where you have this group, all the divisors are attained as orders of some elements in the group. So I will try this. You also try in the meantime using these two things. Let us see if we can solve this exercise without using Lagrange's theorem. You know the solution once you have Lagrange's theorem, and because of that you know the answer also. The answer is just that, all the divisors of 60. There is something else also that can be said that is even more advanced. If one goes to classification of finite groups, since we haven't seen the concept of isomorphism yet, so if you don't know about it, you will find it somewhat difficult to understand. Two groups can look different, but in the background they are same. For example, if you what natural example can I give without making it extremely complicated? Suppose you have, okay, let me just first clean this part. Say you have this set, okay, and say you have this composition table. It's very straightforward and easy to see that under the operation defined by this composition table, this set is a group. On the other hand, you can think of another set whose composition table is like this. Okay, so in this group the operations look like this. EE is E, EA is A, AE is A, and AA is E. In this group the operations look like this. Say we have used to be somewhat what can I say, to be somewhat concrete. Say we have used addition modulo 2 because that's what it looks like. No, this is actually C2. So 0 plus 0 is 0. So that's why I am using plus. 0 plus 1 is 1. 1 plus 0 is 1 and 1 plus 1 is 0. Now looking at these two groups, which are actually extremely different in the sense that they look different, but still there is a sameness. Different because the sets are totally unrelated to each other. The only thing is that as sets they are unrelated because the elements, here we have some abstract elements E and A, here we have numbers 0 and 1. The only common thing is that both the sets have two elements, but after introducing these two operations we can see that there is a sameness if we make an association. If we associate 0 with 1 and E with 0 and A with 1, then you can see that E gives us E, 0 gives us 0. So it's like whatever is happening in one group, an exact mirror image happens in the other group. So one can say that the two groups are, as far as the group structures are concerned, they are basically the same. Now this is the concept of isomorphism. Isomorphic groups may look quite different, but actually they are the same group. There is no real group theoretic distinction between them. If you perform one calculation or if you find a fact about one group, that same fact, or rather once you translate the fact in the language of the other group, which is maybe some other group isomorphic to this one, the fact will remain the same. Okay, that's the thing. Now using this idea, mathematicians have classified groups into isomorphic classes, because group theoretically, since there is no distinction between two isomorphic groups, so there is no point in studying them separately. If you have two groups, say, which turn out to be isomorphic, then you can keep them in one isomorphism class, where other groups which are isomorphic to one another are there. You can keep some other groups which are isomorphic to one another among themselves in a separate class. No two groups from two different classes are isomorphic. So it's enough to study only one from here, another one from here. Now this is a fundamental question in group theory, to classify all groups into isomorphic classes, which of course naturally is still unsolved. Only in some specific types of groups this have been accomplished. For example, for finite simple groups classification has been done. Now why am I saying all these things here? That is because groups up to isomorphism, there are only two groups of order 10. Only two isomorphism classes. One of them has this group and the other has this group. One is our familiar Z10 and the other is the dihedral group D5. Now if one wants, one can use this fact, which of course is extremely advanced, to say something about this group H, because essentially H is either this or this. Okay, but we of course cannot do such things. We have to somehow stay elementary, use only elementary techniques, use only whatever we have got so far, and still solve this exercise. Okay, so let us move on. So this is a failure so far, but we will see. Then the next one is exercise 46. Which of the following numbers could be the exact number of elements of order 21 in a group, in some group 21,600 or 21,602 or 21,604. Okay, so this exercise asks, we are given three numbers. Which of these can be the number of elements of order 21 in a group? So can there be this many elements of order 21 in a group, or this or this? Okay, now in trying to solve this, we need a condition that these numbers should satisfy. We know one result. The result is that if we are in a finite group, then the number of elements of order D is a multiple of phi of D. This result we already know. This is in this chapter itself. However, in a group, not necessarily in a finite group, so that means we should not be able to use this result. However, there is something that In the book itself it's written in the answers, so we can write it here. The argument given in the proof of corollary, proof of the corollary to theorem theorem 4.4. shows that in an infinite group the number of elements of order n, where n is a positive integer, is either a multiple of phi of n or infinite. Okay, so this is a fact that you will see if you go to the proof of the corollary to theorem 4.4. In fact, in this corollary itself, the statement of the corollary is just that in a finite group, the number of elements of order d is a multiple of phi of d. Okay, so what is the conclusion of all these things? If our original group is infinite, then in them the number of elements of order 21 is either a multiple of phi of 21 or is infinite. But if our group is finite, then by the corollary itself, the number of elements of order 21 is a multiple of phi of 21. Now, since it's given, it has been asked that among these numbers, which one is the possible number of elements of order 21. That means our number of elements of order 21 is given to be finite. So that means it has to be by the corollary to theorem 4.4 in case the group is finite, and by this observation even when the group is infinite, this number among these three must be a multiple of phi of 21. Thus, phi of 21, which if you calculate is, let me just show the calculation also. 21 has two prime factors, 3 and 7. This number should divide the number of elements of order 21, since among the given three integers, these three, only 21,600 is divisible by 12, it's the correct number, the correct answer. The others are not divisible by 12. Then I need ink. (47) If G is an infinite group, also here it's given that the group is infinite. What can you say about the number of elements of order 8 in the group, and also generalize? So this is just you can look at the previous exercise. The number of elements of order 8 is either a multiple of phi of 8, which is equal to 4, or is infinite. And this is in the general statement, in place of 8 you just write a positive integer n. That's all. So in the solution we write C the solution to the previous exercise. So that is 47, then 48. Now this is another one which I haven't been able to solve. Suppose that K is a proper subgroup of the dihedral group D35 and K contains at least two reflections. What are the possible orders of K? Explain your reasoning. Here also same problem, we don't have Lagrange's theorem, which seems indispensable for this kind of exercises. Let us, before we leave this exercise, let us just briefly see why we are leaving it or why I am leaving it. You may be able to solve it, I hope you do, or I hope I myself I am able to do it after some more thought. So D35 we know has 35 reflections and 35 rotations. Now it's given that K is a proper subgroup of D35. Okay, keep that in mind. K contains at least two reflections. So those two reflections you can consider as F and F prime. Now we have seen already that F prime is, this is a rotation which is not equal to R naught, because it's given that there are at least two reflections, so that means we are able to choose two distinct reflections. So that distinctness will allow us, by using that previous exercise, to have this non-trivial rotation, and because they are in K and K is a subgroup, so this will belong to K. Okay. Now this non-trivial rotation will generate a cyclic subgroup inside K. So from that you can guess the order of K, and also it is said that at least two reflections. So there may be more, this is the smallest possible. Apart from that, the reflections themselves will generate cyclic subgroups of order 2 each. So looking at everything, you can then try to think of the number of elements that K can have. But again, the same problem, because K has reflections and not just rotations, so K is now not a subgroup of this. Because this is a cyclic subgroup, you already know, it has all the rotations. So K has reflections means K also has rotations, so K intersects this cyclic subgroup, and at the same time K has these reflections outside of this subgroup of rotations. So taking into account everything, you will have to somehow guess the order of K, but at the same time, since K is not entirely contained in this, you cannot use the results of cyclic groups, the results that we have in this chapter. So that's where the problem lies. But maybe I'm missing something. I should not say we are, because I don't know how you are thinking. Maybe I'm missing something obvious. I can't see how one can readily solve this using only whatever we have got till now. Okay, so this is another failure which we will have to come back to later. Then exercise 49. For each positive integer n, prove that C star, the group of non-zero complex numbers under multiplication has exactly phi of n elements of order n. So this is a nice example which shows that the general result, which says that there should be the number of elements of order n should be a multiple of phi of n. This is a particular case of that where the number is exactly phi of n, and this is also true for any positive integer n. So at once we are having all the numbers of elements equal to phi of n for every n. And the solution to this is available in the text itself. But anyway, let's just see what the author has to say. So these are the author's words, okay, not our word or not my word. It follows from example 15. In chapter 2 and example 10 in chapter 0, that this cyclic group generated by this complex number this is a cyclic, of course it's a cyclic group, and this cyclic group has exactly n elements. It is a cyclic group of order n, where all the elements satisfy the equation x to the power n equal to 1. Oh, I should perhaps write exactly what Gallian has written. All the okay. Satisfy the equation moreover since every element of order n satisfies this equation, of course, satisfies this equation, so what? Oh, and there can be, okay, and there can be at most n solutions. Just give me a moment. There can be at most n solutions of this equation because it's a polynomial equation of degree n, so at most n solutions. So all the elements in the group of non-zero complex numbers of order n belong to H. All the elements in H already satisfy this equation. Okay, we are not saying that does not mean that all the elements in H have order n. That's not what we are saying. We are just saying that all the elements in H satisfy this equation. Okay, and any element in C star that has order n must satisfy this equation. But now from the equation itself we can see that there can be at most n solutions to this equation. So that means since we already have n numbers here in H, all of which satisfy this equation, so the solutions to this equation have all been captured here inside H. So in particular, among those solutions, all the elements in C star of order n will also be there. So that's why all the elements of order n belong to H. Now we have to figure out how many elements of order n there are in H. And that number is just this. So by theorem 4.4, C star has exactly phi of n elements of order in. Why exactly? For that you see the statement of theorem 4.4 and you will understand, it's very easy. And finally, exercise 50. Prove or disprove that this set H, which consists of all the integers such that n is divisible by both 8 and 10 is a subgroup of this group, the additive group of all the integers. Okay, so for that we can apply one of the subgroup tests. Note that, but before we do anything, we have to make sure that the set we are considering is non-empty. Note that H is non-empty because 0 belongs to H. 0 is an integer that is divisible by every non-zero integer actually. So in particular by 8 and 10 also. Let n and m belong to H. Then n is divisible by both 8 and 10, and m is also, so this is extremely straightforward. Hence, from elementary properties of integers, n minus m is also divisible by both 8 and 10. Why 8 and 10 though? I think in this exercise they play no role other than the fact that they are just some integers, non-zero integers, both 8 and 10, and so n minus m belongs to H. So this is a subgroup of the additive group of integers. So this completes the solution, and here we end the video. So we have been unable to solve two of them. We will remember these two things. We will keep on trying, and the moment any of us comes up with a solution, if you do, please let me know. If I do, then I will let you know. Okay, in the next video possibly, or if that is not possible, then we will just keep on struggling, and things like this will occur. Okay, it is next to impossible that we will be able to solve all of the exercises. Whatever exercise we come across, we will be able to solve them. That is not just next to impossible, that is actually impossible. And since one of you has requested for ring theory also from Gallian, so the next video on Gallian will be on ring theory, and then we will again do group theory. So like this, alternately we will alternate between group theory and ring theory, just like with Herstein's topics in algebra, we are alternating between fields and vector spaces. So we will do that same thing with Gallian. So see you in the next video. So until then, this is me, Lucifer, from a mathematical room. Have a nice night and stay safe also, because the virus is spreading again. Bye.